They belong on posters, walls, and computer backgrounds just as much as they belong on the road. They're supercars. From those that look fantastical and ludicrous, to the no-compromising engineering masterpieces. Everyone that has been entranced by speed and power knows the names Ferrari, Lamborghini, McLaren, Bugatti, Porsche, Aston Martin, Pagani. The list goes on and on. Cars keep getting faster and faster, breaking new barriers every year. This past year, 3 major manufacturers took the next big step in supercar design, using onboard batteries to power electric motors that work with normal gas-powered engines. Yes, the Porsche 918 Spider, the McLaren P1, and the Ferrari LaFerrari are technically hybrids, but they sure don't accelerate like your average Prius. So, what can we expect in the future? The use of science and engineering, nanostructured materials could make the next generation of supercars even faster. Having the fastest production car in the world is a prestigious title for any car manufacturer, which is probably why so many different types of cars have claimed this spot over the course of the last century. In general, the way to make a car go faster is simple. Make it as light as possible, and give it as much power as you can. So, how do you make a car lighter? By using engineering know-how and newly available lighter materials. In the 1950s, this new material was aluminum, rather than the steel that had been used previously. Aluminum weighs 1/3 as much as steel, meaning that cars that used it in their construction had an immediate weight advantage over their steel counterparts. One of the first production cars to make use of this new, lighter material was the Jaguar XK120, which set the world record top speed for production cars at 125 miles an hour, way back in 1949. This Jaguar used the expensive aluminum sparingly, only using it for the body panels. The Mercedes-Benz 300 SL, with its iconic gull-wing doors, went even further with weight reduction. Instead of using a wooden frame like the XK120, the 300 SL opted for a tubular steel frame, though the body panels were also made from aluminum. This meant the Mercedes was a full 300 pounds lighter than the Jag, reaching a top speed of 140 miles an hour when it launched in 1955. Lamborghini Miura is considered by many to be the world's first supercar. Instead of putting the engine in front of the car, Lamborghini opted to put it right behind the driver. This allowed for better weight distribution as well as optimal aerodynamics. The Miura weighed as much as the XK120, but made up for that fact by more than doubling its horsepower to 350, provided by a huge V12 engine that rocketed the Miura past 170 miles an hour. The year was 1966. The next major breakthrough in car design would come almost 20 years later in the 1980s, with the introduction of a brand new engineering material, carbon fiber. Carbon fiber is much lighter and stronger than both steel and aluminum, something supercar manufacturers took advantage of immediately. The Ferrari F40, a personal favorite of mine, used carbon fiber and Kevlar composites to drastically reduce the weight, while maintaining an extremely stiff chassis. This car is a glorified go-kart, but this go-kart was the first car you could buy that would break 200 miles an hour. 5 years after the F40 came out, in 1992, the absolutely insane McLaren F1 was revealed. Featuring the first ever carbon fiber monocoque design, the F1 not only used carbon fiber and Kevlar, but also titanium, magnesium, and even gold. Behind the steering wheel of this car, you could get to the stratospheric speed of 240 miles an hour. Finally, we come upon the current king of speed. It took over a decade for another production car to take the throne from the mighty McLaren, but the engineering minds at Volkswagen dreamed of a car that could exceed 250 miles an hour. In 2005, they unleashed the Bugatti Veyron, a 16-cylinder, 4-turbocharger, 1,001 horsepower monster. While many engineering materials such as carbon fiber went into the building of this car, the main reason it claimed the speed record was because of the simply ludicrous amount of power underneath its hood. Thanks to new European Union laws concerning emissions and environmental issues, W16 and V12 engined monsters are quickly becoming a thing of the past. Many thought this spelled the end of the supercar as we knew it, with diesels and hybrids becoming more and more common. A few of the top brands of supercars thought differently, however. and used the once dreary moniker of hybrid and turned it into something wonderful. Each of these cars costs about $1 million. They'll all do over 230 miles an hour. They'll all get from 0 to 60 in around 2.8 seconds. They're all faster than even the Bugatti Veyron to 180. And they're all hybrids. So, what does the future hold for the fastest of the fast? Engineering materials even lighter and stronger than carbon fiber could make cars even faster. Larger capacity batteries could output more power, creating a truly monstrous hybrid vehicle. How might these things be possible? Through something called nanotechnology. What is nanotechnology? The first clue is the word nano, which is short for nanometer. A nanometer is 10 to the negative 9th times smaller than 1 meter, which is around 3 feet. A human being is around 1 to 2 meters, or 1 times 10 to the 0 meters. A bee, or a fly, is about 1 millimeter in diameter, or 1 times 10 to the negative 3 meters. Now we start getting really small. A micrometer is 1 times 10 to the negative 6 meters, or about the size of a speck of dust. 1 nanometer, 1 times 10 to the negative 9 meters, is the radius of a DNA molecule in your cells. Now, how small is that exactly? Take a look at this dot. You can barely see it, right? If this dot were 1 nanometer in diameter, and it was part of a brand new supermaterial installed on the body of a car, that car would have to be 12,500 kilometers long. That's about the same size as the planet Earth. Materials on this scale are smaller than you can even imagine, and yet engineers have been working with nanoscale particles for decades now, creating new materials and technologies that could very well build and power supercars of the future. One material that scientists have discovered are called carbon nanotubes. A carbon nanotube is a single sheet of carbon atoms, rolled up into a tube. These tubes are only about 1 nanometer in diameter, but are incredibly strong for their size. When carbon nanotubes are manufactured, they come out wavy and randomly oriented. This is undesirable in a strong material, as it leads to uneven loading of the tubes and premature failure. What you want are well-dispersed, long, and straight nanotubes that will provide a high strength when loaded. A team of engineers has figured out a way to harvest carbon nanotubes from an array and feed them through a series of rollers in order to stretch them. During the stretching process, the tubes straighten into a single direction, causing them to align. Once this process is completed, the tubes are sprayed with a polymer resin and spooled up to create a final composite material that is 50% carbon nanotubes and 50% resin. How does this carbon nanotube composite material stack up against other materials? In order to compare common materials used in today's cars, we have to look at some important properties of these materials. 2 of the most common materials used to build vehicles are steel and aluminum, due to their low cost and high machinability. Carbon fiber is a composite material that is used on current high-end supercars. The last material on this chart is the carbon nanotube composite that we just talked about. Tensile strength is the maximum amount of stress a material can withstand while being stretched before breaking, and is measured in megapascals. The density of a material is given by how much a cube that is 1 centimeter by 1 centimeter by 1 centimeter weighs. Therefore, it is given in grams per cubic centimeter. The strength-to-weight ratio is perhaps the most important property when it comes to car manufacturing. As this number increases, the amount of material required to maintain the same strength decreases. The strength of steel and aluminum are similar when compared to the values of the composite materials, which are 4 to 10 times larger. The story remains the same when it comes to the density of these materials, which, despite their higher strength, have a much lower weight per cubic centimeter. The high strength and low densities seen in the engineered composites mean that the strength-to-weight ratios of these materials are an order of magnitude larger than those of the natural steel and aluminum. What does the strength-to-weight ratio mean in the real world? The average four-door sedan weighs around 1,500 kilograms. If all of the major components, such as the body, doors, frame, trunk, hood, exhaust, fuel tank, radiator, wheels, drivetrain, suspension, engine, transmission, steering, you get the point. All of these are made of steel, that accounts for approximately 830 kilograms of the final weight. if you replaced every single piece of steel in that 1,500 kilogram car with aluminum of equivalent strength, that 830 kilograms goes down to 480. Replacing every piece with carbon fiber reduces the value all the way down to 48 kilograms. And if you used the carbon nanotube composite discussed earlier, all those parts would weigh a mere 17.5 kilograms. The total weight of your car just went from 1,500 kilograms to 690 kilograms, just by using engineering composites.
Sweet!
Lithium-ion batteries are everywhere these days. Hybrid and electric cars, cell phones, MP3 players, Game Boys, Kindles, really any type of portable technology uses these rechargeable batteries. So, how exactly do they work? What makes them rechargeable? You can think of a lithium-ion battery as a sandwich. The bread on either side of the sandwich are the electrodes, which transport the electricity to the places that it's needed. The mustard on one side of the bread is the cathode, the mayo on the other side is the anode. In between these two condiments is the meat, which separates them and prevents them from coming into contact with each other. And all the air in between these layers is the electrolyte. During charging, positively charged lithium ions travel from the cathode, usually made of lithium, through the electrolyte and the separator, and into the anode, usually made of graphite. The graphite stores as many of these lithium ions as it possibly can until it's filled completely to the brim. At this point, the battery is fully charged. During discharging, the battery undergoes the opposite process, and the lithium ions are transported back into the cathode. What if I told you that there were materials out there that could store more of the lithium ions than graphite? Using materials such as germanium and silicon could increase the amount of charge from a battery of the same size as current batteries by 10 times. Imagine a cell phone that lasts 2 weeks on one charge. Why aren't we using those materials, you may ask? Well, I'll tell you. A graphite anode remains the same before, during, and after the charging cycle in a battery. This is great, because it means that it can repeat the process over and over again, going through more than 1,000 cycles before there is any noticeable decline in the performance. Hence why these lithium-ion batteries are rechargeable. Unfortunately for future battery technology, this is not the case for germanium and silicon. When saturated with lithium ions, these materials expand, sometimes by up to 300%. During the charging and discharging cycles, the expansion and contraction of these anodes quickly destroys the integrity of the anode, rendering it useless after just a few cycles. How can nanotechnology help to fix this problem? Nanowires can expand and contract without destroying themselves, unlike a flat plate anode of the same material. Germanium nanowires have an especially interesting characteristic, as they tend to destroy themselves in a very slow, consistent, and positive way. Starting out with vertical stalks of wire that are 1,500 to 2,000 nanometers in diameter, the anode slowly transforms over the course of 100 cycles into a stable, porous network of millions of much, much smaller nanowires. This structure is able to maintain a charge capacity more than double that of even the most efficient lithium-ion battery for over 1,100 cycles. Nanoparticles can also be used to avoid the self-destruction of these anodes. While silicon nanoparticles still expand and contract by 300% under charging and discharging, the particles are so small that they retain their spherical structure. In order to make sure that each of these nanoparticles is electrically connected to the battery's electrolyte and electrode, a team of scientists surrounded the silicon nanoparticles inside an electrically conductive carbon network. Each of these carbon pods contains one silicon nanoparticle, with enough space to allow the silicon to expand under charging. This system provides an anode that can store almost 4 times the amount of charge that a graphite anode can, yet still retains that same charge for over 1,000 cycles, just like the graphite. Through the use of engineering and nanotechnology, the supercars of the future could be something we can't even imagine today. Just think about what you would have thought in 1950 if someone had told you that in 50 years you could buy a car that would go double the speed of the current world record holder. Maybe in 50 years from now, you'll be out shopping for that new 500-mile-an-hour Ferrari that everyone is raving about. Maybe you even helped engineer the materials that built it. Hopefully, that car looked something like one of these, instead of like this.
There we go. Reliant Robin.